All right, welcome to part two. So this one will look at second and third laws just a little bit, and more than anything, it just looks at a different way of solving for delta S, for entropy. So just a slightly different way of solving these problems. So second law of thermodynamics. It talks about the relation to the entropy of the universe, which I slightly mentioned on the last slide a little bit, or the change in entropy of, for the universe. So if it's a reversible process, that should equal 0. If it's an irreversible process, like dropping an egg, which is probably also spontaneous, the chaos in the universe is going to be greater than 0. The universe should become more chaotic, not less. So the universe should equal the system plus the surroundings. You're not going to look at it this way a whole lot. The big detail here is just that if it's not a closed system, then you have things that are being lost to the universe in some way, which is why in general we talk about things as a closed system, because if it's a closed system, then there's no universe involved and everything is staying right here. It's staying inside of the systems and the surrounding, and not lost to space. This is also just kind of a slight note on things. So on a molecular level of things, you can have translational movement, which is when the entire molecule is moving from somewhere else. So gas particles do this all the time. Gas particle moves from here to across the room. Vibrational motion is literally when one atom in there is vibrating. This happens a lot when it's exposed to infrared radiation, so that's heat. When something heats up, a few of the atoms in a molecule vibrate and heats up. Rotational motion, this happens when you stick something in a microwave. So if you put it in a microwave, you're going to, the microwave's designed to spin the water molecule, so it spins the hydrogens on the water molecule, which heats it up, which causes your food to be nice and warm and tasty. So that's rotational motion, so it's just spinning. This is just looking at how temperature relates to entropy. So as temperature increases, you can see that absolute entropy is increasing. So gases have more chaos than liquids that have more chaos than solids. Okay, third law of thermodynamics. If you look at this from a physics perspective, there's a lot of math involved, but really what it ends up boiling down to is the nature of absolute zero. All we're concerned with as far as the third law is basically that anything at absolute zero has zero entropy, because there's no motion, there's no energy left. So if you have a substance at absolute zero, it has zero entropy, but we will never ever get anything to absolute zero. So that being said, you will never see a zero value for entropy. So S as a value should never be zero, and that will come up again later on here in one of these further slides. Okay, predicting the sign of delta S, so this is just kind of like the last video, so we can kind of quickly do this here. We have a solid on this side reacting to make a solid plus a gas. So we've generated a gas which is far more entropy than the solid. So here the expectation is delta S is going to be positive because it became more chaotic. Chaos. Down here we have 4 total moles of gas reacting to make just 2 moles of gas. So this system is getting way more organized, so delta S is going to be negative because it went from chaos to order. Okay, so this brings us to standard molar entropies. So everything that we're going to use to solve the next type of entropy problems is the standard molar entropy value, so this S naught value. Just like we had H naught before, so when we did heat of formation, so enthalpies of formation, we can do something similar with entropy, so we can do standard entropy. Expectations. Gases are going to be greater than liquids or solids. It should increase with increasing molar mass. So the more complex the molecule, the greater the delta, the S value should be, and it will also increase with the numbers of atoms in the formula. Also, big thing here. It will not equal 0. So when we did H values, if it was an element in its natural state, it would have a 0 value. That is not true for entropy because that thing still has a level of chaos to it. So this is going to be the big mama equation. So products minus reactants. So you guys saw Big Mama equation before when we had the H values. This is version number 2. So same idea, the sum of all of the S values for all the products minus the sum of all of the S values for all the reactants equals delta S. And you have to pay attention to N, which is the coefficients. So here we have a reaction. We can predict this guy because we have, again, 4 moles of gas here, 2 moles of gas. So the prediction is that delta S here is going to be a negative value. We have this table that has all of the values in it, so we can kind of break these up. So looking at the products first, the products are going to equal 2 because of this coefficient here, times the value for NH3. So NH3 is right here, so 2 times 192.5. And then reactants, there's 2 reactants, so we have to deal with both of those. So 1 times the value for N2, so 191.5, plus 3 times the value for H2. So 130.6. So then we can do, so S is going to equal P minus R. So in this case, grand total for this guy is negative 198.3. And if you notice here, this value is definitely going to be larger than this value. So I didn't put this negative in, the math just came out with this negative. So this time the value will come out to what you're expecting. So it will come out with the sign you're expecting, but it's a good way to double check. So here's a couple different problems. This one talks about using the appendix in your textbook. I already pulled those values out for you. So products, values for all the reactants. So plugging and chugging, delta S is going to equal 2 for the value of aluminum, plus 3 times the value for steam, minus 1 times the value for this aluminum solid, plus 3 times the value for this gas. Also, if you look here at this one, it's kind of hard to predict because we have 3 moles of gas here, 3 moles of gas here, 2 moles of solid, 2 moles of solid. We're getting a positive value. This is a fairly complex structure. There's nothing quite as complex over here, and we have more moles of solid. So that's really why we're going with that's why we're getting this positive. But it's not an easy one to predict. So prediction-wise, this one's a bit harder to predict. Okay, so looking at both of these, well, let's try to predict them really quickly, and then you guys can kind of solve one of these out, and the bottom one I will just give you the solution to. I won't actually solve it out. So here, 2 moles of gas to 1 mole of gas, so the expectation is delta S should be positive. Or sorry, delta S should be negative. Come on, Travella. because it should be more organized. And then down here, 2 moles of gas going to a solid, so also delta S should be negative. So breaking those up, here's the very first one. Again, use the Stoich coefficient. So products, here's the sum of reactants. So there's that negative value. Down here, we're getting that negative value. So hopefully, if you guys tried that one out, you should have gotten the same value I did. So much shorter video. Hope this makes sense. We will talk about this in class soon, and not much left but delta G. So talk to you guys later.